Hi everyone, today we're going to be talking about attributes of rational functions, vertical asymptotes, and how to find them, what are they, how do we do them on an equation, or how do we do them by graph. Okay, so let's get started. First of all, what are vertical asymptotes? Okay, I'll be showing you different graphs on different functions, but in essence, here we have a rational function. This is my x-axis, my y-axis, and I'll draw this graph, an example of a rational function. Okay, one that has a vertical asymptote at x equals 1. Okay, now what happens here with vertical asymptotes is that we have these imaginary lines where the function is never going to touch. It will approach it, but it will not reach it. And it'll happen at specific locations in the graph where the function is determined or has become undefined. And here it happens at x equals 1. What happens in these functions is that whenever you try to divide by something that gives it equal to 0, it becomes undefined. You cannot divide anything by 0. At that point, the number does not exist. We call it an undefined term in mathematics, right? And that usually happens here in this example. I'll show you this function is going to be f of x equals 1 over x minus 1. Okay, if I substitute this 1 into this value of x, we are left with f of x equals 1 over 1, 1 minus 1. Okay, 1 minus 1 is 0. So dividing by 0 in this equation is not possible at this location, right? So what we say is that this function is undefined at the point x equals 1. So because we cannot divide by 0 at that location, the function is going to get really close to that vertical asymptote in both directions, right? On the bottom side and on the positive side, it'll get really close, but it will never actually touch it. Okay, and I'll show you some examples here in a minute with Desmos and how you can zoom in and try to see how it's trying to touch and approach this line, but it will never reach it. Okay, so a vertical asymptote happens when you try to divide a function by 0, and most of them will have different types of asymptotes. You can have one asymptote or two asymptotes. Okay, here when we plug in 1 into the equation, 1 minus 1 turns into 0 in the denominator. We cannot divide by 0, and that's why the vertical asymptote here happens at 1. So let's start with an example. If we cannot divide by 0 in the denominator, then what we're going to want to do is we're going to want to be able to solve for x in the denominator. So the step that you're going to actually do and take over is set the denominator equal to 0 and solve for x. When you're solving for x, just for the denominator, right, you move the other numbers to the other side, and you get x equals 4. So this tells me that there's going to be a vertical asymptote at x equals 4. So my graph will look something like this, and I'll share with you in a little bit what it looks like on Desmos. So at 4, 1, 2, 3, 4, we will have a vertical asymptote. An imaginary line the graph is going to try to touch, but it will never reach. Okay, so my graph will look something like this. Okay, notice how here the graph is going to approach the line on the top and in the bottom, but it will never actually touch it at x equals 4. Let me show you the example here on Desmos so you can see it. So if I move this over, let's change this function to x equals x minus 4. Notice how here there is an imaginary line that you cannot necessarily see that I'm going to type it in as a dotted line. Okay, so in Desmos, I'm going to type in the function x equals 4, and I'm going to make this a dotted line so we can see it better. Okay, see this dotted line that the graph is trying to approach? Now, it looks like it might even touch it somewhere here on the top. So I'm going to move this function downward and see how as I go towards the top, if I try to zoom in a little bit, there's actually always going to be a gap between the line, the imaginary line, and the function itself. And I can try to zoom in as many single times but you will never see that they actually touch. It'll get close to it, but it will never reach it. And that's really what this vertical asymptote is. The function is going to try to touch or approach this number. It's going to try to get to 4, but it'll never actually get there because at 4, it doesn't exist. Okay, so here's an example with one vertical asymptote. Let's try one with two vertical asymptotes. Notice how the denominator here, we have a quadratic. So whenever we set the denominator equal to 0 to find our vertical asymptotes and we're trying to solve, now when we're solving this function, we're solving one with two possible solutions, right? So because it's a quadratic, I'm going to do my 3 columns. I have 4 times 1, right? Notice how I can cross multiply, and when you cross multiply again, you get 1x and 4x, and that definitely adds up to 5x. So my factors here are x plus 4, x plus 1. So I can rewrite this function as x divided by x plus 4 times x plus 1. That's just written in factored form. Now, I'm still trying to figure out what the denominator is set equal to 0. So I'm going to set it equal to 0 individually. I have x plus 4 equals 0, and I have x plus 1 equals 0. And when I solve, I move the 4 to the other side. On the left side, I get x equals negative 4. When I move the 1 to the other side, I get x equals negative 1. So here I have two vertical asymptotes, one at negative 1 and one at negative 4. And I'll show you what this graph looks like in a little bit. But anytime that you have two vertical asymptotes, a lot of different things can happen, okay? So I just know here that my graph is going to look like at negative 4 and at negative 1, I will have two imaginary lines that the graph is going to try to touch. Okay, and I'll show you what the graph looks like here in a second. So we pull this over here on the side, and we pull it over with Desmos, we're going to get x over x squared plus x plus 4. I have two vertical asymptotes, one at negative 4. Right, you see this imaginary dotted line that's existing here, and there's another one that's going to happen here at negative 1. I'm going to type that in as well. X equals negative 1. It's dotted and blue, so we're consistent. So notice how here, okay, we have two imaginary lines, one here at negative 4 and one at negative 1, which means we have 1, 2, 3, 3 intervals or 3 locations here that we're looking at in terms of parts of the graph. The more exponents you have in the denominator, right, like x cubed, x to the 4th, x to the 5th, the more possible vertical asymptotes you're going to have. Now remember, it's going to try to touch the line, but it will never reach it. And it might look like it's touching it here, but if you zoom in, you will always be able to find that there's always going to be a gap between the two lines, the red one and the blue one. Okay, so graphs get way more exciting. The more denominators you have, the more exponents you're going to be dealing with. But the rule here, let's review the rules real quick. No matter what you're dealing with a vertical asymptote, no matter what function it is, no matter how crazy it is, the rule is you set the denominator equal to 0. And the second step, solve for x. So if you have just one x in the denominator, you set it equal to 0. If you have x squares in the denominator, you're going to set it equal to 0 and solve for two x's. X cubed, x to the 4th, no matter what you have in the denominator of a function, okay, whatever your function is, regardless of whatever you have on top, it could be really crazy, and the denominator, you set the denominator equal to 0. When you set that bottom part equal to 0, that's the part that's going to give you the vertical asymptote. The imaginary line that the graph is going to try to touch, but will never reach. All right, guys, I hope this helps. If you have not subscribed, go ahead and do so right now. And as always, we'll calculate later.